Good to see everyone here. My name is Tim Gaskins. I'm from the region that we're going to be looking at today, which is Oxford, Alabama. In October of 1996, Hurricane Opal graced this area with her presence, and she left me with my first memory of a flood. Because of the severity of this storm, my parents drove my baby brother and I to my grandparents' house to take shelter. My most vivid memory is of the cellar door flying open and the amount of wind and rain that was outside. At the young age of 4, it was the most powerful thing that I had ever seen. The morning when I woke up, though, I was treated to my first flood experience. Their entire backyard was flooded as it had rained about 7.5 inches during her stay. As you can see here, their property backs up very close to a regulatory floodway. I recently asked my grandfather about this since I was so young at the time, and he told me that he was lucky because there was only about 6 inches of water in his shop that was in the backyard. The image of that backyard, which to me, up until that point, was a beautiful, fun place to play, suddenly full of water, with enough water that their neighbors were able to canoe in the back as they checked on people, will always stick in my mind. Luckily, my grandparents only had a tiny amount of damage because their house itself was elevated enough to where there was no water in it. But as FEMA says, just 1 inch of water can cause $25,000 worth of damage to your home, so there was some significant damage to that shop. But luckily it was just a shop. In more recent years, the Anniston Oxford area has experienced significant flooding, resulting in the loss of lives, the endangerment of vulnerable populations, the disruption of services, and substantial damage to properties and critical infrastructure. In 2019, multiple households had to be rescued from Jerry Avenue in Oxford. If you look at this imagery, you notice multiple buildings inside the regulatory floodway. I don't know the hearts and minds of the people living there. I don't know if they were ill-informed or if they knew that they were in a flood zone, but if you know you're in a flood zone, one of the best things you can do is have a plan. There was apparently no plan in place for the people that lived here, so they had to take up the resources of the city. They had to take up the fire department that had to go rescue them, and then they also lost a lot of very valuable things. As people, we need to be prepared for not if, but when a flood comes. While accurate flood forecasting contributes significantly to the reduction of fatalities and damages, a very important contribution is the generation of flood maps and the estimation of flood risk. However, flood maps alone don't assess the risk to people, property, and the infrastructure in case of a flood. Simply put, the impact of the flood is at the minimum if the flooded region is void of people, property, industries, and socioeconomic activity. Therefore, the socioeconomic factors are critical for risk assessment. Risk assessment is the result of the combination of hazards, exposure, and vulnerability. Due to the need to mitigate flood risk in urban areas, we have selected the Oxford-Anniston area to demonstrate and test the proposed methodology. Anniston and Oxford is one of the most vulnerable metropolitan areas in Alabama due to both its vulnerable population and its physical setting. Another reason why we chose this area is due to the increase of developed areas. If you look at Calhoun County, there appears to be an area with more of a development than others. These areas are Oxford and Anniston. In the upper catchments of Calhoun County, we are experiencing an increase in deforestation, which will affect the runoff that will go down towards Anniston and Oxford. So for evaluating this vulnerability, we selected the census tracts that touch the Anniston-Oxford city limits. We collected our data from multiple agencies, which include GSA, USGS, Calhoun County GIS, and ESRI. Our goal with this study is to have the local authority realize that this estimated risk is managed by taking measures to reduce the exposure and vulnerability of identified urban elements to the flood hazard zone. We want to help them become more aware of this and in turn help the community become more aware as well. I would like to note this isn't still a preliminary study. It will be continuing over the next few months or maybe even longer. And I'll get over into more detail of what we'll be working on in the future here soon. To continue developing our data, we took the DEM and processed it to find both the slope and the land depressions. A depression is where the landscape, big or small, is lower than the surrounding area and it traps water. It causes puddles. Maybe you know of a low area in your own yard that just holds more water than others. That is a depression, and we looked for those. We also took the buildings in Calhoun County and found all of the large buildings. We did this by finding the average of the buildings, or the average size of the buildings, finding the average of the buildings over that average, and then finding the average of buildings over that as well. That give us almost 1,000 buildings to consider in Calhoun County. The exposure spatial layers contain the physical components of the urban system, which are buildings. Primarily, everything is covered in concrete. It takes away from that natural drainage that the ground has. And these elements can be acquired from various spatial databases. The flood hazard spatial layer consists of areas that are susceptible to flooding, such as water bodies, impervious areas, areas of low slope, and land depressions. And this is calculated by the means shown here on the screen. These have been obtained by the land cover map provided by USGS based on Landsat's imagery. Social vulnerability is basically the ability to evacuate or move in the case of a flood. Based on 5-year estimates from the American Community Survey, social indicators such as age, household income, education, employment, single-parent families, minority populations, and those who rent their home were determined. The vulnerability and susceptibility of population to damage resulting from the flood hazard is estimated based on many different socioeconomic parameters. The following slides that we'll look at here will focus on those vulnerabilities, which were normalized by dividing each category by the population. If you would like to notice, you will notice a trend there. You will notice a trend around right here in the center that will be focused on by these maps. With the low-income families, they are very focused right here in this area. More unemployed people are focused there as well. It's a little higher up there for high school diploma or less. There's a lot higher place right here in the non-English speakers, which would be downstream, which if the floods continue. People who are under the age of 5 and lower are there as well. And the residents over 65 was actually out of the flood hazard area, where they're actually in a lot of higher elevated areas. People who rented their homes were near that area, and single parents were also very vulnerable in that area. So how did we find the total vulnerability? Well, we added up all these social vulnerabilities per tract, then we multiplied that by the sum of the exposure of the tracts. This gave us the total vulnerability. The spatial risk index for each census tract within each flood hazard zone has been estimated using a spatial layer overlay operation between the hazard and the spatial layers of flood consequences. The consequences layer was generated based on the spatial intersection of the vulnerability and exposure layers. Spatial intersection was performed using a raster multiplication operation. An index value for each grid raster cell was estimated and ranked based upon the index values that we generated. Based on the preliminary results, we observed consistency with a limited sample of reference data indicating known flood-prone areas. Further validation is required, of course, but we hope to use this in collaboration with the relevant flooding management authorities. One of the best ways that we will make sure that this data is correct, and one of the best ways that we can make sure that what we pass on isn't wrong in any way, is by using one of the newest things that JSU has gotten us. We have recently obtained a LiDAR, a drone recently obtained a drone which has LiDAR and a multispectral camera which we can use to collect data. It has a laser and camera instrument. It provides an accuracy of 6 centimeters when you're 40 meters off the ground, and it flies 3 meters per second. This camera helps collect data in ranges of light from visible to near infrared to thermal. It has very high spatial resolution where you can get many different mixed pixels, and it gives us a higher accuracy where we can really determine where the flood damage will be by observing the ground, how permeable it is, what's around it. Basically, using this example here, we're going to know that this ground here where the driveway is, it's going to hold water a lot more than all this grassy area and the trees and a natural runoff. So using this LiDAR data, we can remap and reevaluate the FEMA flood maps. We can identify floods with very high accuracy before it happens, because we know these are the areas that are least permeable. These are the areas where more people live and will be susceptible to it. In this respect, LiDAR can provide an early warning system to the areas with a higher risk of exposure. And we want to accurately measure how high the floodwaters will be in the buildings and the infrastructure. to give people this knowledge ahead of time instead of waiting until it actually floods and then they're already in danger. Thank you for your attention. A huge thank you to the geography department and everyone that helped me. As an older student returning, they really made me feel welcome, and that was really great. My wife says I'm happier, so I'm just extremely thankful for all the work that they've done with me. Thank you.
So the LiDAR, I assume it's like an extension of radar, but what's the LI? What is it, or is it?
It's basically using light, that infrared, and
light.
yes, you basically. How did Dr. D can describe it much better than me? Basically, the ground looks different than the concrete, or the permeable ground looks different when it reflects back that thermal light and it reflects back that kind of stuff, and it can tell you the difference in it.
Yeah,
Real
that makes sense.
easy way to describe it.
You can tell the difference between different surfaces.
Because it's a light reflection and not the radar.
It's a light detection and ranging is what LiDAR, I just did.
Thank you.
Light detection and ranging. Okay.
They have a Holiday Inn Express last night. So how often should we be doing updates on this kind of stuff? Is this every couple of years, every 5 years? Like what's?
It really, in my opinion, it depends on the rate of urbanization. If an area is making not as many houses, making not as many industrial areas, you don't have to update it as often. But if you are in an area where houses are sprouting up everywhere, where businesses are coming, you're going to need to update that more often because there's a lot more concrete now. There's a lot more places where water doesn't really have a place to go. So probably at minimum 5 years, probably more often depending on the area.
I'm just thinking about the factor of climate change on top of it, where even if your city is the same, maybe the climate is changing on you.
Yes, sir.
That's a lot of factors.
Forestry uses it too to determine the health of forest and that sort of thing, the different light reflections.
It's really cool. Cool. All right, thank you again.